is the last lecture, and I'll actually talk a little bit about this stuff finally. So here's the outline of what we've done so far. We had a couple lectures on electromagnetism and quantum mechanics, and we had a series of lectures in particle physics, and we met the standard model and said a few things about supersymmetry. Then after that, we turned our attention to gravity, and we talked about curved space-time, basic problems of why quantum gravity is hard. The last time was the first time we actually met string theory, and now finally talk about, well, making connections between string theory and our world is a sort of gigantic subject. There's lots of people working on it from many different angles. And obviously what I'm going to present to you today is sort of my own point of view and my own bias. And just to remind everybody, there's no lecture last week, so don't come last week. So when I was putting this lecture together, I have to say actually there's some things in the handout that are not in the lecture anymore. I removed them. When I was putting this lecture together, I decided that it might be nice to have sort of a brief summary of some of the important points from the earlier lectures, including this one. So I actually devoted a pretty good chunk of this lecture to sort of summarizing some things that we've said before, maybe the first 15 minutes or so. But they're part of the sort of message I want to bang home throughout the lecture. So we met a while ago, we met this beautiful thing, the standard model of particle physics. It had all these great simple set of ingredients that does a great job of describing the physics that we see. And we have the electron and neutrino electrons and some other partner particles that are a little bit like them. We met the quarks. The quarks were these constituents that made up all the particles in this particle zoo that Galvan introduced. And we have these force carrier particles that are associated to 3 of the 4 fundamental forces of nature. The photon of electromagnetism, the gluons of the strong nuclear force, and the W and C bosons that carry the weak nuclear force. And one of the beautiful things about the standard model was that these forces were all very different. Electromagnetism was a very long-range force between charged particles. The weak nuclear force is a short-range force that mediated radioactive decay, and the strong nuclear force behaves differently from both of those in the sense that it was very, very strongly coupled and takes quarks and glues them together into bound states of protons and neutrons. But even though these forces were so fundamentally different in how they appear, we could describe them all in a very simple way in this picture of force carrier particles in exchange. So we have this wonderful picture of physics coming from that. And the standard model, then, we noticed, was kind of miraculous. At some point, we talked about doing calculations in the standard model, and we said, okay, if you want to study, say, the interaction of an electron with a photon, you have to sum over all histories. That's what we learned from Feynman. If we measure an electron going in and going out interacting with some photon, we don't really know what's going on in the interior here. It could be this, it could be something more complicated, where the electron spits out a photon, it could be something even more complicated, and we had to sum over all of these things. Yeah, and we saw that this led to one of the problems of particle physics, or one of the aspects of particle physics, that when we do these calculations, we would get infinity. We got divergent answers. And, well, why is that? What was the old paradigm that when, quantum field theory and particle physics are smarter than we are, if we do a calculation and we get an infinite answer, it means we've done something wrong. And in this case, what we did was we assumed, we sum over histories, we allow these particles that fly around that never go out and are seen by our experiments. We allow these particles to achieve arbitrarily high energies. That carries an assumption with it that we understand what physics at high energies is. And that assumption is just plain wrong. This description of physics is not correct for physics at arbitrarily high energy scales, and the infinities was representing that fact. So we had to introduce parameters to parameterize our ignorance of what that short-distance physics was. And the miracle of the standard model was that even though we had infinities all over the place, and we could have been very sensitive to the unknown physics at short-distance scales, miraculously, the standard model only depends on that unknown physics through 19 parameters. So, the standard model has a number of particle masses and couplings. We don't know why they are what they are, but they represent their parameterization of how the physics of the standard model depends on what's happening in very, very, very short distance scales. So we saw all of that, and then we turned to gravity, and there's no such miracle for gravity. We tried to introduce the notion of a graviton, just like we had the electron as the sort of smallest piece of an electromagnetic wave as a force carrier particle. We thought we can quantize gravity by taking these gravitational waves, these ripples in space-time, and looking at the smallest piece of a gravitational wave and identifying that as a force carrier particle and just proceeding like we did with all of the other fundamental forces. So we would have an electron interacting with a graviton, and this would lead to some long series of corrections. And we encountered 2 problems. One problem is that the miracle of the Standard Model didn't happen here. It was short distance physics that gravity was sensitive to, and it was sensitive to it to an infinite number of parameters. With nice 19 blew up to infinity, so it's extremely sensitive to unknown short distance physics. You know, we can think of that heuristically in a simple way by thinking that whatever physics is happening at short distances, it may or may not interact with electromagnetism or the weak force or the strong force. But gravity's different because gravity couples to everything. So whatever's happening at very short distance scales is going to couple to gravity, and gravity is going to depend on what the details of that physics is. So gravity was extremely sensitive to the short distance high energy physics that we don't understand. But it had a second problem that's not unrelated to the first, and that was that the interaction strength of gravity carried a mass dimension. It was this thing, the Planck scale. And when we did computations, we found those computations were organized in a series in this dimensionless ratio of energy and Planck units. What this meant was if we did experiments at very low energies compared to the Planck scale, and I remind you that a GeV is about the mass of a proton, so this is 1 times 8 with 18 zeros times the mass of a proton, roughly. If we did computate, or did try to do computations at very low energies, like where the LHC is, a few of these terms would be okay. We just need to make a few measurements to fix a few parameters and we'd be fine. But if we wanted to really honestly study physics as we approach the Planck scale, then we start needing infinitely many of these terms. And at some point when we reach the Planck scale, every one of these constants here is a 1. The whole theory breaks down. So just like we saw with Fermi's theory of beta decay, we can go ahead and do calculations up to the Planck scale, but when we get up to the Planck scale, the whole thing falls apart and the framework just collapses. And the indication of that is that this is not the right way to think about gravity at high energies or short distance scales. And then we were stuck. And, well, this is a really horrible place to be stuck because the Planck scale is right where all the interesting physics of quantum gravity take place. As we saw in the lectures on the information problem and so on, gravity has some very odd features we don't see in the other fundamental forces of nature. There's a breakdown of naturalness. We saw that quantum effects can become important even when curvatures are small. Even at the horizon of a black hole where the curvatures are small, forces are small, quantum effects could be very important. We saw a breakdown of locality, the fact that quantum states can spread over large distance scales. So in order to understand these features better, we need to be able to describe gravity at arbitrarily high energy scale, and our theory of graviton exchange just doesn't work for doing that. So we arrived a couple lectures ago at this point. We needed some inspiration or some thought to make progress in understanding gravity. We needed a new idea. And last time we introduced as that new idea string theory. Now, I talked a little bit about string theory and how it came about historically last time. I'm not going to do that now. But I'll just tell you remind you the basic story. The idea of string theory is a pretty simple one. You just suppose that any point particle in nature, if you zoom in, isn't really a point particle at all, but it's an extended object. This extended object is fundamental. It's not made of smaller things. It's just an extended object. And it says that, the objects of nature have energy or whatever that extends over some distance scale. Now, this extended object can wiggle in many different ways. It can wiggle like this, it can wiggle like this, it can wiggle like this. And an observer like us, who's not equipped with such a magnifying glass and can't zoom in close enough to just see the difference between these wiggles, will think a string wiggling like this looks like one kind of particle, and a string wiggling like this looks like a different kind of particle. So every different way the string wiggles responds to something that we would interpret as a different kind of particle. And one of the miracles we talked about last time is that something that looks like a graviton comes out automatically. One of the ways that a string can wiggle describes a particle that will mediate a gravitational interaction. I mentioned at the end last time that computations in string theory have no infinities. They don't have the infinities of the Standard Model. And that means something important. That means there's no unknown short-distance physics that we have to parameterize. We don't have to introduce any parameters to reflect ignorance of short-distance physics, because string theory just makes sense at all energy scales. We just do computations and we get answers. There are no free parameters. It's basically just this thing, the string tension. So I'll remind you in the Standard Model, all the parameters, the masses, the interactions, all that stuff, those things were just parametrizing things we didn't know about physics at short distances. String theory doesn't suffer from that. String theory has no problem describing physics at all distance scales. So it very nicely gives us a description of quantum gravity that works at all distance scales. And everything, at least in principle, can be calculated directly. I threw this slide up last time. how does the vanishing infinities happen? And roughly the idea is that a point-particle interaction gets replaced with something that's a little bit more spread out. When 2 point particles come and interact, they interact at a well-defined point in space-time. And if you think about an electric charge, and you think about trying to calculate the energy of an electric charge, and the bad behavior you get at the very singular point while that charge is, those field lines are coming from, you can imagine that the idea of an interaction at a well-defined, distinct point in space-time might lead to some bad behavior. And that's really it. In strings, when two strings interact, the diagram looks like this. A couple strings come together and they mesh into one. There's no single point where the interaction is happening here. It gets smoothed out. And that smoothing out is what leads to the better behavior at short distance scales. So we have this nice picture where we have a theory that makes sense at all energy scales. It describes quantum gravity. Because it gives many different particles corresponding to the different ways that the string can wiggle, it can in principle describe the particles in nature. So you can ask, what's the catch? And we talked last time that the big catch is that string theory requires extra dimensions of space-time. And we talked about this a little bit last time, and I'll just say that the string, in order to have a consistent theory of strings, the string has to have a certain number of excitations. There has to be a certain number of ways that you can add energy to the string that are sort of different from each other. And it's natural to think of every different way that a string can wiggle as corresponding to a different direction it can wiggle in space-time. So a string moving in our 3 dimensions can wiggle in 3 ways. It can wiggle up and down, or left and right, or back and forth, whatever. There's sort of 3 ways that you can, different excitations of the string. Quantum mechanically, we require more, and the natural way to interpret those is as wiggles in extra other space-time dimensions. So the picture we arrived at is one that looks like this. Every particle in nature is really a tiny vibrating string, and we have these extra dimensions, and we had to take these extra dimensions and follow the Kaluza-Klein idea and curl them up on some geometry. So if you take any point in our world and you zoom in very, very close, you will see that there aren't really 4 directions you can move, but there are many other directions that you can move, which curl themselves up onto some complicated looking geometry like this. And, well, the 4-dimensional physics that we see depends on what this geometry is. It depends on what's going on here. In some sense, you can think of this geometry as specifying the details of the short distance physics, in a sense. If we zoom in closer and closer distance scales, eventually we'll see that these new dimensions open up. And the details of what those new dimensions are in some sense the details of the short distance physics that we don't know in the standard model. So while the equations, the string theory was a unique theory, it didn't have any parameters. The equations of the theory were unique. Those equations admit many, 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 many solutions. And that was sort of the problem. These equations emit many solutions. So there's many different possible ways that the extra dimensions can look. And we like to hope that there's one way the extra dimensions look that leads to 4-dimensional physics that looks like this, the standard model. So there's one set of extra dimensions that leads to our old friend, the standard model of particle physics. But there are in principle many other choices of extra dimensions that lead to, God knows what. Could be anything. Could be, well, a lot of stuff you can get there. So the next question you can ask is, what are the possibilities for the extra dimensions of string theory, and start enumerating them. So let me draw a point for every possible choice of the extra dimensions that string theory can have. Here's 16 points. So this point corresponds to maybe curling up the extra dimensions on a geometry like this. The second point is the extra dimensions look like this, and so on. I ran out of different diagrams, so you can just imagine. But as you look closer, you realize that there's not really 16 points. There's actually more. There's many, many, So every one of these points is a different choice of what the extra dimensions could look like. So if you look closer, you find more. Maybe there's more choices. And if you look closer, you find even more and more choices. And at some point, the number of choices becomes so big that you can't see the spacing between these dots anymore, and it just looks like a big blur. And, it looks like a big blur. And the reason it looks like a big blur is because you can estimate how many choices there are for the extra dimensions, and the number that people come up with is around 10 to the 500. Now, in the past, I've tried to explicitly write these numbers out sometimes when there's zeros and 1 and put all the zeros in, but if I tried to put a 1 followed by 500 zeros, it would probably take up more than your slide, so I decided not to do it. But it's a huge number of choices. You should think of this sort of blob as a collection of individual dots. Each dot is a different choice for what the extra dimensions are. But there's so many of them that we can't even see the spacing between the dots, so we just draw a blob. Now, we give a name for this thing. We like to, This is very complicated. It makes our life very complicated. It means that there's many possibilities for the physics that come from string theory. We'll get into all the complications of that. But we like to feel good about things, so we give it a nice name. We don't draw a blue blob. We can put a picture here of some nice mountains, and we call this the landscape. There's actually some better reasons for calling this the landscape, but I'll just say I like to call it the landscape because landscape's something nice, so I like to think it's nice. So you should think when I draw this picture, you should think what's really sitting here are a collection of points, and every point is a different possibility for what the extra dimensions are in our world. And every one of these points is different choice of extra dimensions, and a different choice of extra dimensions would give rise to different four-dimensional physics. So you can look at this horribly complicated picture where there's 10 to the 500 different possibilities for the physics that comes out in 4 dimensions. And you can ask, how can we hope to learn anything about our world from this horribly complicated picture? And this is where we left last time. How can we hope to learn anything about the physics of the world in which we live? So when you think about this problem, it's kind of a daunting problem. There are sort of two, a lot of people who work on landscape physics. People, work from many different directions on this stuff. But most of the things that people do can really boil down to one of two questions. The first question is, where are we? We like to think that our four-dimensional world corresponds to some choice for what the extra dimensions are. We have one choice for what the extra dimensions of space-time look like, and if we look at the physics from that choice, the physics from that choice describes our world. And, well, trying to nail down where we are in the space of 10 to the 500 possibilities is a very daunting challenge. But that's one of the questions. The second question you can ask is, why are we there? Why did our world pick this choice for the extra dimensions instead of one that's over here, or one that's over here, or one that's over here? Let me say a little bit more about what these questions are. The question of where are we is more specifically what shape do the extra dimensions take in our world, and how can we tell? And, well, if we can tell, can we crank out any predictions about our world from that knowledge? The question about why are we there is a little bit different. It's more like asking, why do the extra dimensions in our world look the way that they do? And is it an accident? Are we here instead of here by some freak accident in nature, or is there a good reason that the extra dimensions look the way that we do, and our world looks the way that it does? And is there a physics reason for that? Now, I'm going to give you my opinion about these two questions. And this is a very practical question in my mind. It's a practical question that seeks to understand the physics of the world in which we live. We'd like to understand our world. Our world corresponds to some choice of the extra dimensions of string theory. So we'd like to understand what that choice is, figure out what it is. This is a little bit of a cheap shot. It's not, it's getting a little closer to philosophy. There's real physics you can do here, but it's a little bit closer to philosophy because the underlying question that people are after with this socket is why the physics of our world is what it is as opposed to something else. And so there's some questions over here that can be made sharp. There's some questions over here that, in my opinion, are not so sharp. If you've heard anything about the multiverse or the anthropic principle, that's all on this side of the picture, trying to figure out why the physics of our world is the way that it is, why we're at one point as opposed to some other point on the landscape. Now, in the first version of these slides, I went through a few iterations of this. The first version, I actually had a section on the anthropic principle, and I cut it for reasons of time. But there's a page in the notes about it. There's at least something about the anthropic principle. But I don't want to say anything too much about the anthropic principle because that's, at some point these lectures are a little bit about what I do, and that's not what I do, and there's actually a good reason I don't do that. I don't particularly like that. My opinion, my bias, I'll tell you. So the question I'm always focused on is the first one, which is where are we? We have all of these choices for the extra dimensions of string theory. We think that one of them corresponds to our world. So we like to know which one. We like to figure out, where we are. And to reiterate, the question is, what do the extra dimensions of our world look like? And in principle, and in particular, what can we learn about them if we experiment? Anytime experimental measurements are done, we're learning more about the physics of our world. And that is in some way telling us something about the extra dimensions of our world, and we like to know what that information is. Now, if you want to attack this problem, it's not very practical to look individually at each string geometry. You can imagine picking a random point from this set of 10 to the 500 and studying it. If you get the part of physics of our world, you stop. If not, you pick another point. And you just keep going. And that's just not practical. 10 to the 500 is way too large a number. And I think some people who do complexity theory have proven that picking our world out of this in such a way is something called an NP hard problem. So you dead anyway. So instead what we try to do is we try to pick regions of the landscape, like some collection of extra dimensional choices, like maybe up here or up here, and build models that describe those large regions of the landscape. So we build a model for what all the models of all the geometries up here should look like, a model for what all the geometries over here should look like, a model for what all the geometries over here should look like, and we look for patterns and general features in those models. Even that can be very hard and very complicated because the extra dimensions of string theory satisfy some complicated consistency conditions. And I wanted to tell you a little bit about them because they're amusing. And they have, of course, fancy names. One of them, his fancy name is moduli stabilization, and the other fancy name is tadpole cancellation. And the tadpole's a pretty nice little creature. I don't know what it means to cancel one, and it doesn't sound like a nice thing to do to a thing. But we do it anyway. So I'll talk about the first thing, the issue of moduli stabilization first. And that has to do with the following. Remember that we saw that space-time is dynamical. Gravity is all about the curvature of space-time. Graviton was a gravitational wave, which was a ripple of space-time. And the same is true of the extra dimensions, too. The extra dimensions of space and time are also dynamical. So the extra dimensions of space can vibrate. They can wiggle. Their shape and size can change. They can deform. Now, you can imagine if let's suppose at some point in space, the extra dimensions are wiggling a little bit. When they wiggle, that wiggling carries energy. So a four-dimensional observer who can't see the extra dimensions is just going to see some little localized excitation of energy at a point. So that observer is going to think that this localized bit of energy is actually a particle. So to every way that we can deform the shape and size of the extra dimensions, a four-dimensional observer will see a particle. And, well, that's a problem because the types of particles you get from this happen to be particles that we don't see. We don't see any of these particles. So it's a bit of a problem. So, if we have a choice of extra dimensions that's supposed to describe our world, we have to find some way to freeze the size and shape. Some way to keep the size and shape from deforming easily. Because if it deformed easily, it would give rise to particles that we don't see. And the fancy name for that is to stabilize the moduli. Stabilize is basically just freezing, and moduli is just the technical name for the particles that correspond to deformations in the size and shape of the extra dimension. So the way we do this is we turn on some electric and magnetic fields, or something like electric and magnetic fields in the extra dimensions. So I added some field lines here. Now, these aren't really electric and magnetic fields, and actually we encountered a type of this field last time. If you remember, there was string theory had a particular kind of field that was sourced by strings and not by point particles last time, and that's an example of one of these. So we introduce an analog of electric and magnetic fields along the internal directions of space-time. And these have an interesting effect. If I try to change the size of these extra dimensions here, then I'm going to change the length of the field lines. So the interplay between changes in the shape of the geometry and all of the electric and magnetic fields that are on the internal dimensions cause any deformation to carry an energy cost. In order to change the geometry, we have to add energy to the electric field. So because it costs energy to excite one of these deformations, a four-dimensional observer will see that as a massive particle. And if the mass is big enough, then the particle is something that we haven't seen yet. So our basic strategy is to take these extra dimensions and introduce electric and magnetic fields and other objects too, in order to introduce an energy cost to changes in the size and shape. But this is going to bring me to the second problem, because not every choice for the electric and magnetic fields is possible. You have to be careful when you're turning on electric and magnetic fields on a geometry like this that's curved up. And that brings me to the thing that's called tadpole cancellation. And I want to try to explain the basic idea with a simple example. So imagine taking a sphere, like the surface of a basketball. And I want to think not just putting electric field on a sphere, but I want to imagine trying to put an electron at the tip of the sphere, a charged particle at the tip of the sphere. Well, the electron is going to generate an electric field with field lines that emanate away. And these field lines are going to keep going and going and going, but on the sphere they have nowhere to end. See, an electron, just in ordinary four-dimensional space, it emits field lines, and we can ask the question, where do they go? There's an answer. They go out to infinity. There's a notion of infinity that the field lines can go through. If we try to do the same thing, putting an electron on a sphere, there's no infinity. Sphere is a compact object. There's no infinity. The field lines can't go off. There's no infinity for them to go off to. So all these field lines will extend down to the South Pole, and then they'll all collide each other in something horrible. So what that's telling us is we can't put an electron just on a sphere. We have to put an oppositely charged particle here that can soak up all the field lines. For every source of fields, an electron is a source, we have to have sink, like an oppositely charged particle that will connect to field lines in the opposite direction. Tadpole cancellation is essentially the same idea. It's saying that if you put fields on a curled up space, the field lines have nowhere to end. So they have to all reconnect with each other in a way that's consistent. And that's what we mean by tadpole cancellation. These field lines, I drew it a little bit consistent like this. These field lines are going around a little circle here. They're going to have to come back. And that's allowed. If this geometry was more complicated, I wouldn't be able to put these field lines here. So there's some set of consistency conditions that generalize this problem of putting particles on a sphere that tells us that the field lines all have to have essentially sources and sinks. So our problem is to find some combination of electric and magnetic fields that turn on that freezes all of the shape and size deformations, but at the same time is internally consistent. And this is a very, very difficult thing to do. Now, you might wonder why this is called tadpole cancellation. I couldn't help myself. I had to draw the figure. There's a Feynman diagram associated with this kind of thing, and the Feynman diagram looks like this. And you look at this and you say, oh, it looks like a tadpole. That's it. I should have drawn a penguin diagram. There's a thing called a penguin diagram that shows up that has nothing, it looks nothing like a penguin. It was one of these things where a guy had a bet that he could use the word penguin in one of the papers. So anyway, it's very difficult to do this, to freeze the shape and size deformations with a consistent set of field lines. Which means just building, we have this huge landscape, all these possible extra dimensions of string theory, but building one that you can get your hands on is very hard to do. And in fact, the number of examples where people have carried this program successfully, actually constructed an explicit geometry for the extra dimensions, put in a consistent set of electric and magnetic field lines, and check to make sure that all the shape and size deformations are frozen in a way that's totally theoretically consistent. The number of examples is very, very small, and depending on who you talk to, may even be zero. I think the number is small and non-zero, but it's very small. It's a very hard thing to do. So how do you proceed? Well, there's a couple of ways that you can make progress. And both of the ways basically use the same strategy. As opposed to trying to build one geometry at a time, we try to build a model for what a large class of geometries would look like if we were technically skilled enough to build them. And, well, there's two ways you can go. There's one way that goes by the name of bottom-up that will be clear in a minute. And that way, what you do is you focus on trying to study the standard model, how the particle physics comes out of string theory. And you don't worry so much about these shape and size problems. You assume that if you pick enough geometries that have the standard model, there'll be at least a few in there where the shape and size problem can be dealt with. And the other approach is the opposite. You build a model that describes geometries that solve the shape and size problem, but don't worry so much about the details of where particle physics come from. You just imagine if you have a huge collection of geometries that solve the shape and size problem, there's bound to be a few in there that get the standard model right. But in each case, what we're doing is we're picking a region of this landscape, a collection of possibilities for the geometry of the extra dimensions, and just trying to build a model to capture its general behavior. So instead of studying one point at a time, we study one region at a time, which seems a little bit different. So I wanted to say a little bit something about these two approaches. And, I'm actually going faster than I want to say something about these two approaches. And I'll start with bottom up. And by the way, we finally got into the 10 minutes of this lecture series that's on what I do. Ha ha ha. So people who work on this, and I work on this, look at a particular region of this landscape that goes by the name of actually type 2 intersecting brane model or something. Doesn't matter. You just pick some little region of this landscape, some collection of points that could describe the extra dimensions of string theory. Remember, every point here is a different choice of the extra dimensions, and you just look at some region. And the thing that we like about this particular region is a patch of the landscape where we can separate particle physics from the shape and size complications. And I'll tell you a little bit why that is. Well, the reason has to do with the properties of this particular patch of the landscape. As always in string theory, gravity comes from closed strings. This is something I didn't say before. But when I say that string theory always describes the graviton comes from the excitation of a closed loop of string moving through space. And the key property of a closed string is that a closed string can propagate freely throughout space-time. But in this corner of the landscape, the standard model particles don't come from closed strings. The standard model particles come from open strings. They come from bits of string that have endpoints. And there's a sense in which you can think of the endpoints as carrying charge. So, you can think of the electric charge as having something to do with the charge on the end of one of these strings. Now, I haven't fully told you about how this part of the string landscape behaves until I've told you what the ends of the string are allowed to do. Are they allowed to move around willy-nilly? Are they allowed to move around in sort of any direction that you could imagine? And the answer is no. The strings have to end somewhere. There are distinguished surfaces on which the endpoints have to sit, to which the endpoints are confined. We give a name to these surfaces. I can't believe that I'm on lecture 9 and I'm just introducing these things. Well, you can't believe it either. But anyway, I'm just introducing them. They have a name. They're called Dbranes. And for people who know about differential equations and so on, the D stands for Dirichlet. So all you have to do to think about a D-brane is it's just a place where these open strings are allowed to end. I just declare that the open strings can't go anywhere. They have to end on some surface. And the upshot of that is that the open strings are not free to explore all the dimensions of space-time. So the general picture of models like this looks something like this. You can imagine if here's a cartoon of the 10 dimensions of string theory, and the branes extend in some dimensions, but not all of them. So what that means is that the open strings, you can forget about branes if you like, it just means that the open strings are stuck here. Open strings can't move out here, they're stuck here. So the open strings are stuck on the branes, and the branes extend along the four dimensions that we associate with our world. That's good because it means that the open strings that the standard model is coming from can move in all the directions of our world. And the open strings can move in some of the extra dimensions, but they can't move in all of them. And that's the key property. So let me just draw a cartoon for what these backgrounds look like. So we have some choice for the extra dimensions of string theory, and then somewhere in here there's a little distinguished patch where I say that things called branes live. And what that means is that the open strings, if I zoom in on that patch, the open strings are all sitting here. The open strings can't get out here, they can't get out here, they just all sit here. And that's a very nice feature because the string carries a tension. If I want to be able to probe the geometry out here, then I have to do an experiment enough energy that the string can stretch out here in the first place. But the string carries a tension, and that tension is very large. And what it means is that if I do an experiment at some particular fixed energy, the string is only free to extend a certain distance into the extra dimensions. So for example, the LHC is doing experiments at very low energies compared to the string scale of things, which means that in any experiment in the LHC in which these particles, the particles coming from these strings are interacting, any such experiment, the strings are not stretching very far away from this little region. So they don't see most of the stuff that's going on out here. Now this gives, one of the things I like about this gives a very clear picture of why gravity is so hard and the standard model is not. All the degrees of freedom of the standard model, if we say they come from open strings, all of them depend just on the bit of the geometry that's in this picture, in this circle. Because again, the string has a tension that sticks it here. If I don't do experiments at very high energies, then the string can't stretch very far away from this circle. The string is stuck in here, and so everything we see at the LHC, for example, is dependent only on what's going on in this little circle. Now, this little circle is just a small piece of the geometry, and it happens that we can approximate it with roughly a finite set of parameters. So I said the standard model only depends on short-distance physics through 19 numbers, and this is a similar kind of picture. The open strings only depend on a small part of the extra dimensions, And that small part of the extra dimensions can be parametrized by roughly a finite set of parameters. Gravity is totally different because it comes from closed strings, and their closed strings can move freely throughout the entire extra dimensions. So if I do some experiment, some scattering experiment, no matter how low the energy is, if I produce a graviton, that graviton is free to propagate all like crazy throughout these extra dimensions. And the result of the experiment will depend on the details of those extra dimensions. So while the standard model is only sensitive to part of the extra dimensions, gravity is sensitive to every last detail of the extra dimensions. And from a four-dimensional point of view, describing the whole geometry corresponds roughly to an infinite set of parameters. So this is a very clear picture of why gravity behaves so differently from everything else in nature. So it's why I really like this picture. And the upshot of this approach is that particle physics doesn't care about the full geometry. It only cares about what's happening near the branes. It only cares about this region of the local geometry. And it leads to a powerful statement. Any copy of the standard model, any choice I make for these extra dimensions that has the standard model in it, is going to have a stack of branes, and it's going to have a geometry near that stack of branes that looks in a particular way. And the geometry, while the choices for the full extra dimensions are vast and complicated, the choices for the geometry in this little circle are not. They're well understood, they're quite highly constrained, and if we study them, we can make general statements about wide swaths of the string landscape. So the general idea of this procedure then is, we know that regardless of what the extra dimensions are, if the standard model is there, there's going to be some branes, and the physics of the standard model is only going to depend on what happens near the branes. So we just study what happens near the branes. We build a model, and then we build a model of what happens near the branes. There are going to be some parameters in this model that tell us about how it depends on what's going on in the extra dimensions. Okay, those are some model parameters. If we find some interesting physics in our model, then we start asking about phenomenology. We start asking about implications for collider experiments. And we produced a few models of what we think, models we're thinking on the standard model that could be tested at the LHC, and by the way, aren't ruled out yet. Although I'm not going to go on very much about the particular models that we produced that came out of this framework, because there are reasons that I don't particularly like them very much. There's two kinds of physicists, right? As a physicist, if you come up with a model, you can just fall in love with it. Think, this is my model, I love this model, and you put blinders on almost, there's things wrong with it, you just don't, you don't pay attention to it. Like, you're pushing my model, this is my model, I love it. There's another kind of physicist where you come up with a model, and every time you think about it, all you see are the flaws. You see what's wrong with it. You see that this doesn't work, and that doesn't work. And I'm very much the second kind. So I really, we have these flaws. The models we get from here have some flaws, and I can't get past them. So I don't want to talk about them too much. Although I say they're not ruled out yet. They're not ruled out yet. But there's the flaws are theoretical flaws. There are some theoretical parts of them that aren't very great. But those models were just part of what comes out of this braid framework. There's a lot more work to do here, and we're trying to do it. So, but notice the general idea. We don't pick a geometry and just study it. What we do is we find the part of the geometry that's important, the part that describes particle physics, and then we build a model for it. And what we get in this way is not a description of particle physics in a particular geometry. We get a description of particle physics in a large class of geometry. And that allows us to make some progress in understanding the problems of the string landscape. So now I want to talk about the second approach, which is top-down. There's a whole bunch of stuff that can go into the name top-down. And what I decided to talk about is something that I'm a little excited by, but also that you've probably heard something about in the popular press. And so I wanted to talk about it in order to really tell you what's going on and what it really is. So because this, you'll see. So the idea here is we don't worry so much about the standard model, but what we do is we try to build models for geometries that solve the size and shape problems. So we need to find a geometry such that the size and shape deformations are frozen. We're not going to build a particular geometry, but we're going to build a model that we believe captures some of the features of geometries that do solve the size and shape problem. And then we're going to bang on these models with every constraint we could think of, from string theory, from phenomenology, from cosmology, everything. So, as I said before, every change in the shape or size of geometry corresponds to a four-dimensional particle. If the geometry is able to wiggle or fluctuate in a particular way at some point in space-time, there's an energy localized there we think of as a particle. If there's an energy cost to turning on that fluctuation, we think of that energy cost as a mass for the particle. So we do get particles from the inner size and shape, but they have a mass. And while there's an interesting general result, and now I have to put an asterisk here, there's a whole lot hiding in the asterisk. But if I'm going to use the word general, I have to put asterisk. And I can talk about that later at the luncheon maybe. The gravitino is heavier than the lightest of these particles. So we can't make these particles arbitrarily heavy. They can't be heavier than the gravitino. And I have to tell you what the gravitino is. I didn't tell you what the gravitino is. We encountered supersymmetry several times. Oh, this slide has a mistake in it. It says gravitino where it's going to show up in a minute. We've encountered supersymmetry several times. We said that supersymmetry associates to every particle a superpartner particle. So we have the partners of the quarks, which are the scalar quarks or squarks. So the partners up, I guess, would be the sup, and the down for the down. And I mentioned before, I don't know what we're supposed to call the superpartner of the strange. It's strange or something like that. But we have the superpartners for the electrons and superpartners for the force carriers. But if we have a graviton, then we're going to need a superpartner for the graviton too, and we call it the gravitino. So the gravitino is just the new partner particle to the graviton in a supersymmetric model. And these guys basically said that the gravitino has to be heavier than the lightest of the shape and size particles. And that's pretty important, because there's a bound on the mass of the shape and size particles from something I'm not going to have time to talk about. But you may have heard about in the last series of lectures from Mark, I'm not sure. It's called Big Bang nucleosynthesis. It has to do with a model for how the heavy elements are made in our universe. It's a model that works very well, and it's a model that really gets totally destroyed if you start adding new particles. I'll just leave it at that. So there's this magic bound from cosmology that comes in and says the shape and size particles all have to be at least as heavy as 30 TeV. And well, if I told you the gravitino has to be heavier than the shape and size particles, it means the gravitino has to be heavier than 30 TeV, which is very heavy. And to give you an idea of scale, the LHC, when it's operating as well as they think they can ever get it, is going to be at 14 TeV. So none of this stuff can be made at the LHC. Now, the fact that the gravitino is heavy has some implications for other superpartner masses, but those implications, how general they are, I don't really know. So I don't want to make any statements about how general they are. But I do want to say that people have studied this kind of scenario in a model, and that model is called this thing I'll call the G2 scenario, which basically what they do is they pick a different patch of the landscape. Remember, we picked some models up here. They pick some models down here. And these are models for things called G2 holonomy manifold. I won't get into what that means. It's just some other choice of the extra dimensions. And they build a model for what the physics they expect from this corner of the string landscape should be. I will comment, not only are very few geometries constructed, in this example, no geometries are constructed. Nobody's constructed explicitly a single choice of the geometry of the extra dimensions here. All we have is a model for what they should look like and what the physics should be that we think is reasonable. But it's a model. It's a model that's meant to capture a region of this landscape, and nobody's actually constructed a geometry, and there's actually a reason for that. I don't know if you've heard of it. These geometries are about, in terms of actually building geometries, the extra dimensions of string theory, I would say that this collection is about the hardest. It's about the most difficult, and it's extremely complicated. There are many reasons for it. But it just so happens that the properties of this thing means that it's pretty simple to build models, and the models that come out are pretty simple. And the model has a couple of interesting features, and the features are that because the gravitino is heavy, most of the new superpartner particles are also heavy, around 30 TeV, can't be seen by the LHC. But the other feature of these models is that the force carriers are lighter. They're around a TeV and may be seen at the LHC this year, we don't know. And I'm told by the people who work on this, who obviously have a built-in bias, but I'm told by the people who work on this that the dark matter signal I referred to not too long ago also can be a promising feature of these models. And the reason I wanted to talk about this scenario was to flash this next slide at you because you've probably heard about it. There are claims around in the blogosphere and popular science and all that string theory has predicted the Higgs mass. And that prediction, such as it is, comes from this plot, which comes from this set of models. The one caveat I will say is I can tell you firsthand, I was in the audience when the first version of this plot was shown last August, before any of these Higgs rumors came out. So when people say that they did this before they knew what the answer was, they really did. So that's not a really valid criticism. If you take this sort of model based on this sort of G2 stuff and apply a whole bunch of extra phenomenological constraints, and some assumptions, then you arrive at some picture for what the Higgs mass is. And I'll just point out that every point here is a different choice of the parameters they model. They had two sort of disjoint regions of parameter space, one that was bad, one that was not as bad. The bad region was nicely the red points, and the good region was the black points. And you notice the black points like to cluster around the Higgs mass of 125 GeV, and that's roughly where the thing was, or where the bump is. So if that turns out to be the Higgs, then these guys can claim to have predicted the Higgs mass. But there is the question, is this a prediction of string theory? And the answer is not in the classical sense at all. What these guys did was they took a model for what the extra dimensions could be. It's no geometry constructed. They just took a model that was expected to capture the features of some of the extra dimensions, and then they hit it with every constraint they could think of. Constraints from generating this Higgs bath that we saw that we needed to give all the particles mass. Constraints from cosmology. Constraints from collider surge condition. Constraints from consistency of their framework, which was supergravity. Actually, very little string theory went into this. The only real string theory is the assumption of extra dimensions and the structure of the model they used to describe it. So we hit it with all these crazy different constraints and put them all in a blender, and out pops this. And this is really not a prediction in the classical sense that people usually mean prediction from string theory. But it does, in my mind, reflect the way that we have to start thinking about doing physics with string theory. And that brings me into the last 10 minutes, where this has been a pretty technical lecture series, especially the last couple. I wanted to talk just a little bit about general message and almost a philosophy for the last 10 minutes about how we should be thinking about string theory in the era of the LHC, and in particular also in the era of the string landscape. So I just want to make some comments about the general picture. So we're faced with this problem of string theory describes our world but has extra dimensions, and there's many, many choices for what those extra dimensions are, and somehow the dot got moved. So, the old idea was that we would start with one choice of the extra dimensional geometry and compute everything. And with that choice, that extra dimensional geometry would describe our world. We generate string theory predictions for everything in nature, and we have our theory of everything that everybody wanted. Oh, that's a big cockroach. We have that theory of nature, the theory of everything in nature that everybody wanted. Then we kind of came up across this thing, the string landscape. We realized that this kind of approach is not feasible because there's just too many possibilities for what those extra dimensions are. Now, not knowing where we are in the string landscape, not knowing what the extra dimensions of our world would look like, is really tantamount to just saying we don't know what the short distance physics is in our world. We don't know what physics is like at short distance scale. That's all it is. In some sense, you can think about the geometry of the extra dimensions as just telling us what physics looks like at short distances. If we zoom in and zoom in and zoom in, we'll see some features of the geometry, and it will be one thing or the other. And this is a common problem. It's the same problem we always have. We always know physics up to energy scales that we can probe, and we usually don't know much about physics above energy scales we can't probe, and we have standard tools to try to deal with that. But you can stop and ask, if this is the situation in string theory, where we have all these possibilities and it doesn't tell us about what short distance physics is, then what good is string theory? What did we gain from studying string theory in the first place? And I can put it succinctly, and I think this is clear. We basically traded this, and by the way, there's a lot of string theory games, a lot of other stuff. This is just the particle physics one. We traded this for this. We traded this crazy, crazy, horrible expansion that depended on infinitely many parameters, and had this great for this. And now I drew this in a particular way, right? This is very ugly looking, a lot of equations, horrible stuff. And this is very nice looking. So it looks like we traded something ugly for something nice. And I would maintain we really did, although that's, people have their own opinions on that. And I'll remind you, there were two problems with this picture. One problem was it depended on an infinite number of parameters. So it was extremely sensitive to what the short distance physics was. And the second problem was that the whole framework just broke down at the Planck scale. If you try to do anything beyond the Planck scale, the whole framework just broke. And the reason I emphasize these as two separate problems, even though they're not totally unrelated, is that even if we could guess what every parameter is in every one of these things, if we could guess all the parameters that describe the short distance physics, we still couldn't use them to study physics beyond the Planck scale, because we have the second problem that the whole framework breaks down. So even if we knew all these infinitely many parameters, we couldn't say anything about black holes or the universe Big Bang or anything like that. In string theory, we don't know what the short distance physics is. We don't know the extra dimensional geometry. But if you hand me a choice of the extra dimensional geometry, we in principle know how to describe physics at all scales. So if I go back, string theory takes care of this problem, but it doesn't take care of this one. So in that sense, string theory, at least from the point of view of someone trying to make connection with particle physics in our world, string theory for now anyway is kind of like a framework. It doesn't tell us exactly what physics is like at short distances, but what it does do is it gives us a way to describe that physics at short distances. But that means that if we're going to try to connect string theory to our world, we should do physics with it the way we would with any other framework. And that is to the best of our ability anyway, use a combination of theory and experiment to figure out what the new physics at short distances is. So in some sense, when the LHC does measurements, it's probing physics at short distances, which means it's telling us something about where we are on the string landscape. And we need to learn how to take that information and distill it and use it somehow. In neither of the approaches I talked about here did we pick one geometry and try to predict everything. We always tried to build a model. Here we built the model for what some part of the geometry that the particle physics depended on was. Here, these guys built a model that was describing classes of geometries that solved the size and shape problem. And in each case, you build a model and then you bang on it with as many constraints as you can. In this case, these guys banged on it with a lot of constraints and put a bunch of stuff in a blender and came out with this interesting plot. But we always count on an interplay between theory and experiment. Even string theory should do that. And I'll mention that this is very difficult for string theory because there's a huge disparity in scales. You know, the LHC is measuring distance scales that are basically 10 to the minus 18 centimeters. While the size of a string, our best guess is that it's 10 to the minus 33 centimeters. So there's 15 orders of magnitude to separate here. That's why we have to be clever in figuring out how we build models. It's not easy to take information from the LHC and turn it into any sharp statement about the extra dimensions of our world in string theory. But we can try. And well, you know, the models that we've been doing have made some progress. It may be something like the G2 scenario describes our world. One of the nice things about this, even though there's really, one of the nice things about this is that these guys have made a bunch of statements that are going to be falsifiable within a year or two. And the first thing they said worked out. And if more things seem to be working out from this scenario, what's going to happen? People are going to look at that little patch of the landscape that they're trying to model, that nobody's been successful in building any geometries for, and people are going to work very hard to build those geometries. And let me say, nobody would look at that patch of the landscape without strong motivation. It's very complicated. But okay. And if this G2 scenario was ruled out, then we say, okay, that patch of the landscape gone. Let's try something else. But in any way, it's giving us some way to take what we hear from the LHC and learn at least something about where we are on the string landscape. And so I'm actually going to end 5 minutes early, I guess. I shouldn't have cut all that material. This is my last slide, so I just wanted to say thanks to everybody for coming. I really, really appreciate it. There's no lecture series without an audience. It's been a lot of fun. Here's my summary slide. It's very full, but I had to put the page number in the corner, but there it is. Thanks very much.
Imagine these braids, braids, small. How much what order of magnitude smaller are they than the next dimension?
It depends. That's an interesting question because in these models, actually, that ratio is something observable, and it's something simple that's observable. It's the strength of the interaction of the grand unifying group at the high scale. So it's something that we can physically compute at low energy. And the ratio is about 100.
Ratio of about 100.
Yeah. Now then the question is, why is it 100?
Right.
That depends on the dynamics of how the shape and size definitions are approached. You don't have to answer that.
On your philosophy physics problem, years ago I was in chemistry class and a student tried to get the professor to tell him why. And he said, we can tell you what happens most of the time and how it happens some of the time, but for why we have to go over to the white mule after class and discuss it over pictures of beer.
I like that very much.
Yeah.
That's very good.
Yeah, in your whole lecture, you never talked about the fabric of space. And Michael Green in the again, universe dwells on that a lot. And is
Well-
there a reason?
Well, it's just, you know, the fact that this theory of graviton exchange breaks down is really just a statement that this nice picture of smooth fluctuating space-time breaks apart. So that picture, that cartoon, in some sense, of the fact that the fluctuations in space-time are just becoming violent and crazy and we can't talk about in terms of smooth space-time, that's essentially a cartoon for the fact that this model of graviton breaks down. And it isn't the right way to describe it. It's just, it's a nice, it's, you know, it's a nice part. It's a nice picture that he has.
Because supposedly these braids can stretch the whole universe, and supposedly they also cause the Big Bang.
Yeah, there's a scenario where the Big Bang is some brains, you know, bashing into each other. Yeah, you know, there's lots of ideas for that. I should say that Evil's the expert on this, not me. Cosmology and string theory is tough business. So it's actually very hard. I sort of was little about it, saying, oh, once we have quantum gravity, we can talk about, you know, we can talk about black holes in cosmology. Well, the real thing is we learned a lot about black holes. Cosmology, I think, it's still a work in progress. It's very hard. Okay, if there are no other questions, let's go to the lunch.
Yes, before we do that, I wanted to thank everybody for coming on behalf of the chairman for our 75th Compton lecture series. I also wanted to express my thanks to Joe for agreeing to be our 75th lecture. And I hope to see you at our 76th lecture series next fall. In the meantime, please all of you sign up for luncheon. Return upstairs.